More than 90% of the world's images have no labels, and yet we want a single vision backbone that can handle depth estimation, classification, and segmentation without task-specific supervision. So the question is, can we learn a backbone from a huge amount of images and videos that are unlabeled? And more crucially, can we preserve that fine-grained, dense structure, especially as we scale up? DINOv3 answers yes, and the way it does it, it pairs a teacher-student framework, and it also adds a new gram anchoring loss, which helps to stabilize patch-level geometry over long training. Today we're going to talk about. First, let's talk about the big problem that DINOv3 aims to solve. It's the dense feature degradation that occurs as you scale up. So local patch embeddings can become over smooth, or certain feature can collapse in certain directions, and the performance on dense tasks like segmentation or depth dips, even though global classification looks fine. So why is that? Well, first, the teacher-student architecture. So in the teacher is just a moving average of the students. So if the student starts to lose variety, the teacher is going to inherit that weakness, and the whole system drift towards over smooth features. The second thing is the softmax that happens after the student and the teacher encoder. Sometimes it can be too sharp or too sure, and when it's too sharp, it kills that gradient signal for other clusters in the data distribution. So the network stops to explore new representation. Another reason is that there's prototype imbalance. So few prototypes actually grab most of the samples. So there's an imbalance there, and the diversity collapses again. And the last thing is when you supervise only on the patch without a geometry constraints, then global relationships fall apart. So we're going to talk about that. So how does DINOv3 solve it? Well, it solves it on 4 fronts. It has a centering and temperature schedule. So they're going to soften the distribution early and sharpen them later. So that allows to keep the gradient alive and the learning more stable. The other thing is regularization. They introduce a KoLeo regularizer, which is going to encourage the model to spread the features evenly so that there's no prototype hoarding. Another thing is gram anchoring, and that is going to put some geometry constraints. So patches are going to remain meaningful, and the structure is going to be maintained globally. They're going to mix between the global and the local views so that there's both high-level invariance and fine-grained detail. And so what is the output of DINOv3? You get an image like this, where it's when you put a cursor on a certain location, it's going to be able to identify similar patches. So the same fruit in other places are detected. They're very well segmentation. It's high resolution. And even though the image is complicated, it's able to segment very well fruits of the same kind. So it's able to do segmentation and depth. So just to recap before we move on between the teacher and the student. So in a Dino style self-distillation, you have 2 networks and they look identical. You have the student network. This one is trained with gradient descent, so it actually gets weight updates. The teacher network, that one is not trained directly, it does not get weights. Its weights are actually an exponentially moving average of the student weights. So the parameters come from the student, but the student's learning target comes from the teacher. So the gradients flow in one way, but the actual information, it's 2-way flow over time. So that's an important thing to note. What happened in each training step? The teacher sees one augmented view, and it's the global one. It sees like a bigger image, and it's going to output not a binary classification, is going to output a soft distribution. So instead of a one hot label, like this is a cat or this is a dog, which is very limited in terms of richness, it's going to actually output something much richer, and it's a soft distribution. So it's going to be like 70% cat, 20% fox, 10% dog, for example. The student is going to see a more zoomed in local crop, and it's going to try to match that exact same soft distribution of the teacher. That is the distillation loss. So it's the difference between the soft targets produced by the teacher and the prediction produced by the model. So here the teacher acts as a steady target that the student needs to chase. So the student's weights are updated via backpropagation to reduce that distillation loss. And the student is going to see many different augmentations. And it still needs to match whatever the teacher sees at a global level. So there is no labels here. That's the NO in Dino, no labels. The labels comes from the agreements across all of the views and the structure inside the image and trying to match it with what the teacher sees. So this is way better than labels. These software targets provide much more subtle information about the relationship between the classes. So it's a much more effective way to learn. That's why DINOv3 is a very robust foundation vision backbone. As we said, the teacher's weights are updated via exponential moving average of the student's weights, and that stabilizes the learning process and prevents collapse, which is a big thing in self-supervised learning. So the teacher is going to act as a kind of a more mature version of the representation space. It is not sensitive to new things it sees that might not be good. So it's a more reliable target, and it's going to encode the geometry of visual concepts. And though this structure is going to avoid collapse and give very structured representation. Let's move on to gram anchoring. So when you train a vision model like DINOv3, you don't just want it to copy pixel values, you want it to understand the structure. So we're talking about relationship between patches here. How one patch relates to another patch, so it's going to take into consideration the texture, the colors, regions, the object parts. And we want to keep those relationships stable, and that's really important because we weren't able to do so before as the model keeps on learning and scaling. That's where gram anchoring comes in. It's not about memorizing what each patch embedding looks like, it's about preserving the geometry of the feature space. That's why Dino is able to really do well on depth estimation and segmentation and matching features across the image. So what's a gram matrix? Take an image, split it into patches, and each patch is embedded into a vector. Then we're going to take a dot product between one patch and the other patch. In other words, how similar are these two patches in the embedding space? If you're asking the question, isn't this like self-attention where we take the dot product between the keys and the value? No, in self-attention, the patches decide who to listen to compute a certain representation based on queries, keys, and values. Gram matrix is more of a frozen snapshot of how similar patches are put, and we want to learn that frozen snapshot that becomes our geometry constraint during the training. So why is it important? Well, we've already spoken how the teacher learns meaningful patches and organizes the feature representation in a certain way. The student tries to learn from it, but instead of forcing the student to learn to exactly match each embedding vector, we ask it to match the patterns of relationships between the patches. That's the gram loss. It penalizes differences between the teacher's gram matrix and the student's gram matrix. Now, DINOv3 adds another trick. It's the high resolution adaptation. So in this phase, the teacher operates at 2 times the image resolution. So let's say the image is 224 by 224. Well, it's going to scale that by 2, 448 by 448. That means there's going to be more patches, finer details, and a denser feature grid. But the student still works at the standard resolution, the 224. So what DINOv3 does is that the teacher extracts high-resolution features. Those features are downsampled to match the student's patch resolution, and the gram loss is computed at the student's scale. So that way the student benefits from the teacher's high-resolution understanding, which has sharper local constraints and richer context, without actually having to process all those extra tokens itself. High-resolution synthetic data plus the gram anchoring loss is going to yield sharper attention maps and more coherent feature maps, which is really useful for video segmentation and 3D understanding. Let's move on to synthetic data. So DINOv3 incorporated synthetic data generated by diffusion models into the self-supervised training. So instead of relying on purely web-scale real images, they mix in synthetic samples, and that gives you more diverse concepts. So self-supervised learning works really well, but its scalability is limited by the real data availability and the quality. So by having more synthetic data, it brings in more generalizable features. And with synthetic images, you can actually sample objects that are really rare, like indoor zebras, for example. The backbone is going to be less biased to things like zebras. It always needs to be outside, for example. So this makes the output of the teacher on synthetic data have higher entropy. So there's more diversity, there's less overconfidence. And synthetic inputs, they don't neatly fall into certain clusters. So by making the teacher more diverse, it helps fight feature degradation, which is the main problem we saw at the beginning of the video. The idea here is if they only see real photos, they're not going to generalize as well as if you show them AI-generated mashups. So it's going to force the learning to have more broader rules of form, texture, and composition. So how does the overall training look like? So we're starting with 17 billion images, and then we actually embed those using a DINOv3 encoder. We're going to cluster them into a hierarchical k-mean structure to get the concept. And then we're going to sample a balanced coverage of all of these visual concepts. And we're going to end up with about 1.7 billion images. And then we're going to do the pre-training large scale with the teacher student. We're going to add the gram anchoring loss. We're going to add the high resolution fine tuning. And then we're going to distill it to various model sizes. Let's talk about the iBOT loss. So we just saw how gram anchoring in DINOv3 preserves the geometry of the feature space, making sure that the shape of the patch relationship stays consistent, but the idea didn't come from out of nowhere. So to really appreciate gram anchoring, let's just go back to DINOv3. We had the iBOT loss. So that took the dyno's global alignment and zoomed in view. And instead of comparing the entire images, it compared the patches. So it taught the model to keep local meaning consistent, even when parts of the image were hidden or cropped. So the idea is simple. The student is going to see a masked view where some patches are hidden, like in the masked autoencoders. And the teacher, meanwhile, is going to see the full unmasked view. And so for every masked patch, the student predicts what the teacher would have output for that same region. This is not just about learning global semantics. The student learns local consistency, how individual patches should behave when they reappear in another crop. So basically, what's the intuition here? That even if I can't see this patch, I should still know what belongs there. That's part of the training of the student. Lastly, let's talk about the KoLeo regularizer. In self-supervision learning, in self-supervised learning, especially in the teacher-student setups like Dino, there is one big danger: representation collapse. If you only minimize the cross-entropy between the teacher and the student distributions, the easiest path is for the student to cheat. Basically, it's going to map every image to the same embedding. The cross-entropy drops, but all the diversity is gone. So the network stops learning anything meaningful. That's what we mean by collapse. To prevent that, DINOv3 adds a diversity guardrail. It's called the KoLeo regularizer, and it estimates how spread out the students' outputs are in the embedding space. So if all the features are bunched together, then the entropy is low. If they're spread out, the entropy is high. When the entropy is low, that means the distance between those features are small, so there's higher risk for things to collapse. So by maximizing this term, it keeps the model exploring. It's going to force the output to cover more of the prototype space. So what happens if you don't have that regularizer, without that pressure to keep the entropy high? Then a few prototypes are going to dominate, and then those minor ones are going to fade. So the system quietly drifts towards collapse. KoLeo fixes that. Makes sure the students' predictions stay diverse, balanced, and well distributed, even when the teacher itself isn't perfectly balanced.